Okay, our next speaker is Rodolfo Russo. He's going to tell us about holographic correlators with multi-particle states.
Okay, thank you very much. So let me also start by thanking the organizers for putting together this wonderful conference. And today I would like to give you some results about holographic correlators. And I will be focusing on the two best studied examples of ADS-CFT dualities. So the duality between n=4 superior mills and the string theory on ADS5 cross S5, and the duality between string theory on ADS3 cross S3 cross T4 or K3, and the so-called D1, D5 conformal field theory, which is a two-dimensional superconformal field theory. So we know that when you look at the CFT description, and you work at the large central charge and the strong coupling, the bulk description simplifies, and then you can work with the supergravity. So I will call this regime, large C and large coupling, the supergravity regime. And famously, in this regime, you can look at the quadratic fluctuations of supergravity fields around ADS, and then you can put this in one-to-one correspondence with a particular set of CFT states that I will call single particle states because of this bulk picture. And for n=4, you can think about a trace z square, where z is one of the complex scalar, as the prototypical example of such single particle operator, which is dual to some fluctuation of the metric and the 4 form. But even at this stage, the CFT spectrum is richer because it has to contain also states that are obtained by the OPE limit of these single particle states. So for instance, in n=4, oops, I did something wrong. In n=4, so is this, yeah, thank you. In n=4, you can start with two operators trace z square different points, and then if you bring them together, you find a composite operator that contains two constituents, and these are exactly the multi-particle states that I was talking about. So what I will be doing is to derive explicit result for 4-point correlators in the supergravity regime, where these external states, two of them are single particle states, so things that we are very familiar with, and two of them are double particle states. So object exactly like this trace z square square. So 4-point correlators have been studied a lot in the ADS-CFT dualities since the early days when I was doing my PhD. But very little is known about correlators with external multi-particle states. And they are interesting because they contain new CFT data. They contain data about coupling and anomalous dimension and at strong coupling in the CFT. And they also provide a window on higher point holographic correlators. And again, we know little about them. And they do this by keeping the simpler 4-point kinematics, right? If you want to study immediately a 6-point correlator, then it becomes very messy because you have a lot of conformal cross ratio. So I will present explicit result, both in ADS5 and ADS3. And maybe one of the messages I want to convey is that for this problem, these two examples work very much in the same. They are on the same footing. And maybe I suspect this is quite general also for other ADS-CFT duality, at least when you have a supergravity regime. I will tell you what type of functions appear in the correlators when they are written in configuration space, and I will tell you how they look like in Melling space. So most of what I'm saying is based on work in progress with Francesco Prila and Stefano Giusto. Hopefully the paper, at least some of what I'm saying will appear soon. But it's also based on two previous papers, in particular this one from 2021 with Nate Cheplak, who is also at the conference, Stefano Giusto and Marcel Yost. So the way I will be using to derive this correlator is a bit a roundabout. So instead of studying directly what focusing directly on the correlator I want, I will first introduce a gravity geometry approach and study the correlator with many constituents. Instead of just taking two single particle objects and put them together, I will take the point of view that I take many of them, and I will produce what is called a heavy state that we have heard quite a few times in this conference. And this is a very peculiar type of heavy states. It's often called graviton gas type, and is a bit of an exception from what Jan was saying yesterday, because these are heavy states on which we have very good control. We can put them on shell and we can put them as external states. So I will calculate the 4-point correlator in this regime when the multi-particle states are heavy, and then I will take the light limit of that result and extract from the light limit the correlators I want. So the first thing, I will reproduce the known results among single particle correlators. And then you will see that by just looking at the next order in this limit, we will get the new results about the correlators with multi-particles. So let me start just by doing some examples. So on the one side, you'll see the n = 4 example that I already hinted. So you take your chiral primary operator, the simplest one, trace z², and then you put p copies of it, one on the top of each other. And in doing this OP, there are no singularities because this object is BPS, so all the objects are the same, so you can just pile them up. And on the right-hand side is an example in ADS3 cross S3, so let me not enter into the details. Let me just say that for a long time, we know dual descriptions of these heavy operators. So heavy means when the number of constituents is of the same order as the central charge. Then this object would like to back-react the Forner geometry, and instead of just having a quantum in ADS, you have a non-trivial geometry which is asymptotically ADS. And for the n = 4 case, you can think about the Lin-Luning-Maldacena geometries. They are related to this object, raise z² to the p. And for the ADS3 cross S3, you can think about the two-charge fastballs that have been studied a lot also here in Southampton. Now, at this stage, the only thing I want to mention is that there may be a bit of a clash in what I'm saying, because all these geometries are determined by continuous data, right? Shapes, curves, or in the LLM geometries is just what happens on the LLM planes. While the states I'm writing there, they depend on a discrete parameter, the number of constituents. So actually, Costas, Marika, and collaborators made this dictionary precise, and basically the result which I will be using is that the geometries are dual to coherent states of these operators. So you sum over the number of constituents. And the coherent state has a continuous parameter, and this continuous parameter is related to the geometric description. So when I'm saying I will be doing the light limit, well, you will see that in the last line there is a continuous parameter, this is alpha. Then what I will be doing, I will calculate the heavy correlator as a function of alpha, and then I will take alpha to be small. So, for instance, in the ADS5 case n = 4, you can think about the geometry which is sourced by this shape on the LLM plane. So you know that when the shape is just a perfect circle, you have empty ADS. And this is more or less a bit like an ellipse determined by that curve. And then you see, okay, sorry, that eta in front of the cosine should be alpha. And that alpha is the parameter that appears in the dual heavy state. So when you take that alpha to be small, and then you can Taylor expand in that alpha, the dual heavy state starts with a single particle object, trace z², and then at the next order with a double particle object, and then in the next order again a triple particle object, and so on and so forth. So this is the key idea. If you know something which is generic, depend generically on alpha, then you can do the limit and extract the particular power, and then you will select the contribution of a particular multiparticle state. There is a bit of a subtlety, and that is determined by this parameter big A. So when you look at the definition beyond a single particle object, there may be a bit of ambiguity because there are operators that have the same dimension and the same quantum number that could mix. Right? So you could ask, what is the precise dual state to the geometry that I constructed? What is the mixing, for instance, at the order of double particle operators? Right? And this is something you can determine by doing precision holography following Costa's American collaborators. And you can see that if you take the LLM geometry, you will get a state which is not purely a double particle state as this A different from 0. And recently, Stefano Giusto and a student in Genova clarified that there is another solution that at linear order looks the same, and it was found by Liu, Pop, and collaborators. But the CFT interpretation is much more recent by Stefano, which corresponds to the case when big A is 0. So this was a bit of a surprise, and this surprise we learned also originally in ADS3, thanks also to work by Anthony and Bogdan and Nick Warner. You may have more geometries that at a linearized level look the same, but their CFT interpretation is different exactly for the multiparticle state we are interested in. Today I will be working on ADS5 case with the geometry that is dual exactly to the multiparticle state. Very good. So, okay, this is the stage. And now where do the 4-point correlator come? Well, once you choose a geometry, you choose the heavy state, and then you are free to look at the quadratic fluctuation around this geometry, not ADS anymore, around this geometry that describes the heavy states. And then this quadratic fluctuation describes the insertion of extra light operator on the top of the geometry. So if you look at the quadratic fluctuations around the geometry, you are reconstructing this 4-point function with 2 heavy operators described by the geometry and 2 light operators described by the fluctuations. And then you just apply the ADS CFT rules. In order to find this 4-point function, you take the wave equation describing the fluctuation. You want to solve this second order differential equation by imposing boundary condition. And the boundary condition you impose, you need 2 of them to find the solutions, are regularity and interior. And then you want to impose that the non-normalizable mode describes one of the insertion of the light operator, right? It's this delta function, right? Once you impose these 2 boundary conditions, the value of the solution of your wave equation at the boundary is fixed. You can look at any other point which is not 1, and then you see the response, and that response is nothing else than the 4-point correlator. So this is the way we derive the 4-point correlator for generic alpha. And then, as I said, we can expand over alpha, and then the leading term, p equals 0, is just the free ADS result. The subleading term, alpha square, is this result among single particle operator. And today we will be interested in the p equal 2, which goes like alpha to the 4th. And that's the correlator between 2 single particles and 2 double particles. So this is the diagrammatic interpretation that I just mentioned. And let me say that I think on Thursday, Sasha Tyukov will be talking more about this. So if you want to really see how this Witten diagram arises from the alpha, small alpha expansion, then go to Sasha's talks. I will just skip all the detail and just try to convey the story and tell you the result. So the first line tells you the interpretation at order alpha 0 and alpha 1. And the only thing I want to stress is that all the lines that represent boundary to bulk propagators in the Witten diagrams are included in the geometric description, and the dotted line are the ones that are resummed by the geometry, and then you see just the solid line that represents the two-point function. Basically, you are calculating a two-point function in a geometry. At the order alpha to the 4, which is the order we are interested in, the type of diagrams that our supergravity description resums are the one in the middle, right? So you see I'm depicting 4 external states. 2 of them are double particles, so I just slightly separate them to convey that they are double particle operator. And then you connect them with bulk-to-bulk propagators, just to create Witten diagrams. So the one that we derive from supergravity are all the way you can connect this line with 3-level diagrams, right? So gravity, classical gravity does not know about loops. So we will not be capturing the last diagram, right? The last diagram is a disconnected contribution sometimes, which contains a loop. Is of the same order. You see it has 4 vertices. Each of the vertex gives a factor 1 over n in n equal 4 super-Young mills. So it's all 1 over n to the 4th. But that one is not captured by our calculation. So I'm saying that we captured the 3-level connected Witten diagrams. Very good. So what do you get from supergravity? So you get an explicit result in configuration space that is just written in terms of polylogs of the cross ratio of the 4-point function. So you have log z, lie 2, and interestingly, what we already saw in the paper in 2021 is that the order of the polylog is related to this number of constituents in the multiparticle, so the order of alpha. So if you just stop at order alpha square, where you are supposed to reproduce the result among single particle correlators, you can see that the supergravity result can be written in terms of the D function that we already heard this morning in Romain's talk. So this is a nice check for n equal 4 super-Young mills that it just reproduced known result. And let me just say that historically it was interesting that for the ADS3 case, this way of doing calculation was the first one to produce an explicit result for single particle correlators. Right? Witten diagrams in ADS3 were a bit complicated because of Chern-Simons couplings, right? So nobody really cared to complete the calculation at the time. And so in 2018, just with this roundabout, we found, and you see this last result is an ADS3 example. It's very simple. Of course, after that, this result has been generalized and checked. So what I want to do today is to say what happens beyond the single particle state. And the answer, which we missed in the original paper in 2021, turns out to be quite easy. So what you think is start from the D function. The D function is written in terms of a 4-dimensional box integral, just as a mathematical object, right? And you can easily define a new D function where you take away the box integral and you put another ladder integral, a double box, triple box, right? So this is the definition of this D2. D2 means I put a double box, and this one is D1, just a single box. And then these are conformal integrals. Thanks to work back in the 90s, you can write them in terms of polylogs. And then you can check that the complicated answer that you get from this supergravity derivation can be written in terms of derivatives of this generalized D function where you took away the box integral and you put the double box integral. Right? So this last line is an example in ADS3, which is very much reminiscent of this single particle correlator. You see this D1, 1, 2, 2. It has a derivative with respect to 3, 4 to transform 1, 1, 1, 1 into 1, 1, 2, 2. And this is exactly the structure that we have here. So this is the first thing I wanted to say. The type of function that you see in configuration space are just derivative of these generalized D functions. And in ADS3, we could also check that this holds beyond the alpha to the fourth. So if you look at correlators with triple particle states, two triple particle states and two single particle states, they have the same feature. The same is true for ADS5, but the answer we haven't managed to simplify very much, so it would take a couple of slides to show. It's not very enlightening. So let me move to Mellin space, which is the last bit I want to cover. So thanks to previous works, we know how to perform the Mellin transformation of these generalized D functions, this object with polylog 4. Yeah, that's great, thank you. And it takes that form that is written on the top. So that is the, if you want, the easiest Mellin transform of the object which plays the role of D1111. Very good. Now, once you have that formula, you can just use that formula and plug it in this formula on the bottom and calculate the Mellin transform of this answer. This is the example that I was using for ADS3. And then you see the structure that is written there. It contains a term of transcendentality 4, weight 4, that is multiplied by this combination kappa in terms of polygamma. And yeah, so that's the highest transcendentality for correlators with double particle operators. Then it contains terms with transcendentality 3, and then a rational term. And once you extracted this transcendental prefactor, they look very much like the Mellin transform that you are familiar with, just rational function of the Mellin variable S, T, and U. Now, this way of writing makes things much more streamlined, and I can write the result for ADS5. So this is the correlator between two single particle operators which are trace Z square and two double particle operators which are trace Z square square. And it stays in one page. It has the same structure with transcendentality 4, transcendentality 3, and transcendentality 2. And this way of writing already implements many simplifications between the D functions. Very good. So in view of time, let me make just one final comment before the conclusion. So I mentioned that this is not the full correlator. This is just the connected part. But thanks to previous work, we can now also write the full correlators. So basically, we can go back and add this diagram, the final one, because one loop correlators at order 1 of N4 between single particle operator, you see this is disconnected, is something that involves just single particle. These are known. There are many beautiful papers by a lot of people, Aroni, Aldai, Aprile, Bissi, Drummond here in Southampton, Paul Heslop, Paul, who is here, Zhu. So basically what you can do is just take the usual relation between connected generating functional and the full generating functional, right? So W is log Z, and write the connected one in terms of the full one plus all the disconnected contribution. Then you bring all the disconnected contribution on the left-hand side, and the one involved is the one that you have to evaluate at one loop. So once you do that, you have the full correlator. We performed quite a few checks. Let me skip that. Let me just say that one very nice check match also with work done here in Southampton about multiplet recombination, which should happen at n equals 1 over n to the fourth. And this result that I show you is consistent with the data which was derived before. And so let me jump to the conclusion. So I hope I convince you that a study of the holographic correlator with multi-particle state is possible, right? So we can do it. And I have the impression that the examples and I showed to you here are just the first step, and the story applies more generally. There are a lot of immediate questions that are interesting and doable, right? So, for instance, is there some higher dimensional conformal symmetry like Caron, Wu, and Trin did? Are there recursion relations? There is a hint that you can go double particle, triple particle, right? This fact that you have a structure that kind of higher polylog seems to hint that there is a recursion relation. You can lower supersymmetry. All the multi-particle state I was talking about were half BPS, but in n equal 4 it's very interesting to look at quarter BPS. Quarter BPS states are always double particles. There are no single particles, so that's also interesting. But then there are more general questions that, yeah, I think would be interesting in the future. Thank you very much. Yeah, I can speak up. It's okay, it's okay. Yeah, I can repeat the question, please.
Tell me if I understood this from the beginning. The way you do the calculation is by taking an LLM geometry and doing a fluctuation, right?
Yeah, a fluctuation around, yeah. No, not really the LLM, because, but that's just a technicality. The LLM would have this A different from 0, but it's the same, right? It's yeah, you take a non-trivial geometry, which is asymptotically a DS, and then you have to look at the quadratic fluctuation. So the hard thing is, I mean, I'm kind of hiding all these supergravity details, so you have to first diagonalize the equation, right? And yeah, so I think Sasha will tell you more about this, but the way, the first thing we did is the hard way. You take the chiral primary, and then the wave equation is horrible. It's coupled and mixes fluxes, right? Then we say, okay, let's be a bit smarter. You can look at a scalar descendant of the chiral primary, so you act with supercharges. And then the wave equation is just the Klein-Gordon equation with the Klein-Gordon operator calculating on the metric. Then what we really calculate is not the correlator amongst chiral primary, but with the two descendants. You find the result, and then you integrate the word identity, right? So you say, and that there is already a non-trivial check, right? That your result indeed can be connected to the result of chiral primary with known word identity. In a DS3 it's easy because to this word identity I can compute. N equal 4, okay, we need help from literature. But there is a whole story there, which is, I think it's very nice, but difficult to convey in the talk.
You probably explained that, but a priori you might think that this approximation is not very good because you have this, you take the small alpha limit and you might imagine that back reaction becomes important, and maybe it's because of BPS-ness or something, but what's the argument that this is the right procedure?
Very good. No, very good question. I actually did not explain that. I have hidden in this final line, so maybe you. So there is indeed an order of limit issue, which is, I think, what Jan is referring to. So when I'm taking the state to be heavy and do the back reaction, of course I have in mind that the number of constituents is of the same order of the central charge. If I take that number of constituents to be 2, then there is no reason to believe that the geometry is a good description for that thing, right? What we did is just do it, and you check that it works for p equal 1, right? So it's smoothly connected directly to just the single particle correlator. So once we saw that that works, then we say, okay, let's try to understand what the reason is. And I really think that the reason is what you said, is that because of a BPS condition, right? So what happens is that the ingredients do not interact among each other. So when you calculate the contribution of many ingredients at order alpha square, it's just a combinatoric factors that tells you how many pairs you have between the light operator and the constituents on the heavy operator, time the contribution of just that sub thing, right? So for the non-BPS case, there would be mutual interaction between the constituents that would spoil that. We don't have an example of 4-point correlator calculating non-BPS, but we are thinking to try to do that to show explicitly that in that case, this doesn't work.
Is there any specific to the fact that the field theories are in even dimensions? For you can repeat this, for example, for ABJM?
Very good. Yeah.
Okay, thanks.
That's a very good question. Yeah, unfortunately, I know very little of ABGM, but my hope is that this story is general, right? That, so I think I was in the conclusion hinting, look at other ADS-CFT pairs, and that's exactly what I had in mind. Look at ADS4 to see whether one can find the same type of structure, the same type of function appearing. Yeah, but I think nothing is known there.
Hi. So at the end, you mentioned some consistency checks with the previous results on multiplet recombination. Could you say a little bit about what you have to do to see the consistency?
Yeah. Okay. Thanks for the question. So let me start from the easy thing. So what happened is that you can take your correlator and just go to some particular OPE limit, right? And then if in that OPE limit the first operator exchange is a protected operator, then it doesn't matter that you calculated these things at strong coupling. It has to match with the free theory result. And these were kind of the simple check that we did immediately once we have a result as a possible sanity check. But then Francesco taught us refined checks. So we learn about this story. So the idea is that at twist 4, in n equal 4 superior mills, in the representation 0 to 0, there is actually a protected double particle operator, which, as far as I understand, maybe people at the beginning didn't realize it was there. So that operator, about that operator, people know the couplings at strong coupling, and is exchanged in one of the channel of this correlator. So in particular, it's exchanged in the channel where you take the single particle operator and you bring it close to the double particle operator. So you want to check that in that channel, when you decompose the correlator to select the contribution of twist 4 in the 0 to 0, you reproduce the known data. And it happens in a non-trivial way because there is a cancellation between the free part, which I've not been discussing here at all, and this part, which has transcendentality 4, transcendentality 3. So that took us a bit of time to understand what was going on. But yeah, what was important is it is a test on the real kind of meat of the result, right, with transcendentality 4.
Time